I'm Jeremy Manson. I work at Google on our JDK team, and I'm going to talk today a bit about what we do with OpenJDK at Google. Isn't that exciting? Well, I hope so. We'll find out. So Java at Google. So we have a lot of Java code at Google. And we have an interesting opportunity. I always say opportunity instead of problem. I've kind of trained myself over the years, which is that programmers don't really know what their Java code does. And this is a problem and an opportunity that everybody in this room has, right? You write some tiny little fraction of the code, and there are libraries, and there's JVMs, and there's the rest of the application. You don't really know what's going on. So we want to ask ourselves the question is, what can we do with JVM and JDK technologies to actually help that problem, to try to solve some of the problems that Java users have? It's not just about trying to improve performance. It's not just about trying to produce features. It's about, Java users have problems today that they're trying to solve, and what can we do to solve them with the JDK and with JVM technologies that are out there. So to do this, we built a JDK team at Google. And the JDK team at Google is there to deploy, maintain, and enhance the JDK. We build off of OpenJDK. And it's used by a lot of Google applications. It's used by all of the Google applications that use Java, which is a lot. And when I say Java, I mean on servers and things like that. Yeah. So I wanted to talk about development at Google sort of as a running theme through the talk. There is, and sort of take you through a bit of how Java users actually go from the process of coding and to deployment within Google, and sort of take a couple of digressions within that. So I want to give you a sense of what development looks like at Google. There is a single code base for all of our code, modulo a couple of things that are open source. That means that every Google employee or every Google coder, not every Google employee, very rare that you'll have a janitor checking in code. Every Google coder is checking code into the same code base. And so we have this overall view of one giant code base. There are a lot of zeros of lines of code in that code base. The code base grows really super fast. We have a single test cluster where all the tests run. It goes through the code base, finds the tests, extracts them, and runs the test on behalf of the teams. Every time a coder checks in a test, every time a coder makes a check-in, all of the tests that are affected by that check-in get run automatically as part of the check-in process. And there are a lot of tests. Every time you do a check-in, you're supposed to do a test that goes along with it to test whatever it is that you're checking in. Obviously, that's a good software engineering principle that not everybody follows, but for the most part, that happens. And so there are a lot of tests. There's a single very large cluster management system, so that when you're done writing your check-in and running your tests, you deploy to a single cluster. It's not a single cluster, but a single cluster management system. And there are a lot of Java programs running in that cluster management system. And you'll notice that I say a lot of in all of the slides, and I say lots of zeros and all of that, and hopefully you'll all understand that I can't actually give you a real number.
How do you select the subset of tests that are applicable to that particular check-in?
So the question was, how do we select the subset of tests that are applicable for that check-in? And that is a very good question. The answer is that we have our own build system that we wrote that has its own language, and the build system and the language express dependencies very carefully and very clearly. And so when you make a check-in, it analyzes the dependency graph, says, OK, well, it's these tests that all depend on this bit of code that you checked in, and it runs those tests. Does that make sense?
It does, but can this dependency description become outdated if it's manually maintained, or is it?
It has to be manually maintained, but every time you do a check-in, not only does it do the test, it has to build all of the dependent code. So if any of the dependencies are out of date, the code will fail to build.
I see.
So yeah, I think something I say on a subsequent slide is all builds are done from head, and so that's an important part of it. And so if something fails to build, you end up fixing it very quickly. So this is a really amazing opportunity for people who love this stuff, because we have a single version of Java for everybody. and who was it? Remy was just, wherever he is, he was just joking with me earlier today that if we have a single Java version for this thing, it must be like 1.4, because clearly we would never have been able to update it if there's only a single Java version for it, which is not true. I'm very proud to say. For a while it was true, but we managed to not have that be true anymore. So this is an amazing toy. I think you'll agree. You have the opportunity as a programming languages geek to play in this enormous sandbox. Of course, there's the flip side, which I just mentioned, which is that just trying to keep up with the latest Java version. That's like 3/4 of what my team does at Google. It's just, okay, there was another security release, and we have to go make sure that all of the tests still pass, because that's our job. When we tried to deploy the Java 7 runtimes, 20% of our tests failed. It was that, and we just had to spend 6 months making sure that we tracked down all the incompatibilities with Java 7 and fixed them. And you'd be surprised that when you deploy the JDK on n different servers running in the clusters, it breaks more. People come into our team and they think that the JVM is this rock-solid, unassailable object. And then they kind of get hit with the reality, which is that we are constantly bombarded by people who say, the JVM broke again. You guys do a great job, all of you guys. Just getting something that works as well as it does is not just a minor miracle, but a major miracle. So I'm not bad-mouthing, and just trying to coordinate all this stuff is a challenge. But we do have some time to do some fun things. So as I said, I think I'm going to start a stopwatch just so I don't get too over time. Just as I said, I'm going to talk you a little bit through how we do development and how we've been able to sort of inject the JDK technologies and JVM technologies in a few different places. I'm going to mostly talk about places where we were able to use the JDK in coding and in monitoring when you actually deploy your application. So it'll be a very, very high-level overview of the whole workflow with a couple of deep dives that'll last 10 or 15 minutes. So I was inspired by the Scala talk yesterday to put up some famous, well-known philosophers in there. So does anybody know who this is? No. Yes, it is my child. Excellent. This is actually, representative of the average Java coder, I think. I think it's actually an intern. They get younger every year. No, so yes, you're right. It is my child, and I put her up there because I like looking at her. It's terrible, isn't it? Yes. So as I said, developers work. So let's start from the beginning again. Developers work in this single source code base with lots and lots of zeros of code in it, and they mostly build everything from head. And things are supposed to build at head. And if you've broken it, you get a bunch of automated emails from the system saying, you broke it, go fix it, which is great in some ways. All changes have code review. We have great code review tools. We have for what Gmail is to email, I would say our code review tool is to code review. It is really fantastic. And again, this sort of continuous testing thing, where if you check in something that breaks a test or breaks a dependency or breaks a build, the world explodes and you have to go fix it. So digression 1, which is how can we help with this whole coding thing? And the first thing that occurred to us was, well, now we own JavaC. Well, we don't own JavaC. The JavaC developers at Oracle own JavaC. I've been doing that for the last 3 years. At Oracle own JavaC, but we are allowed to tinker with it. So what do? Well, we do some static analysis. And we've added some static analysis features to JavaC. And that helps a lot with the code understanding that I've mentioned in the previous slide, where you don't understand what your code is doing. It helps to have static analysis. The big caveat is that coders don't like static analysis. They really don't. You get out there, and there have been lots of attempts to deploy find bugs at Google. And for those of you, does everybody know what find bugs is?
A lot of noise and a little signal.
Exactly. So there you go. It's a lot of noise and a little signal. So that's the first problem that people say about it. It's like, what is with this signal to noise ratio in find bugs? It's telling me a lot of garbage that I'm not interested in. It doesn't find important bugs. I guess that's the same as bad signal to noise ratio. It's not exactly the same as bad signal to noise ratio. One of the things that the developer of find bugs, Bill Pugh, has noted, he's come to Google many times to try to make us use find bugs and always left in frustration. One of the things that he's like seriously 4 or 5 times, it's horrifying. One of the things he's noted is that find bugs can find actual bugs in code that nobody cares about, and then it doesn't get fixed. That code doesn't get fixed. So you'll see code that is a very, very obvious bug. You'll see things like if p equals null, dereference p.x. Well, that obviously should have been if p is not equal to null, dereference p.x, and that's a very obvious, easy bug to fix, but it'll be in some error path that never gets run, and the coder won't want to fix it. So that's one of the biggest problems with trying to deploy find bugs that we've had. Another problem that we've had is that people don't understand the bug or know of a fix. People, you sort of get this information spit back out at you, and they look at it and they kind of go, I have no idea what that actually means, and I have no idea how to act on it. I think the biggest problem is that running find bugs is actually outside of a coder's workflow. They actually have to think, either you have to build it into your processes very, very deeply so that you are sure that they're running it every time. But they have to think, usually they have to think, okay, I'm going to go run find bugs now. So coders hate this and they won't use it and so on and so forth. But if you take a step back, this is the eye chart that accompanies every discussion on static analysis, right? Do people really want code like this? And I'm not going to go over what each of these problems is because it's stuff that you guys have all seen before, like forgetting to put this when you have an assignment to a field with the same name as a parameter in a constructor. You forgot to put this over there, right? Or you've got an int and you're shifting over by 32, and that's a stupid thing to do. Things like that. People don't actually want code like that in the code base, right? It's a bad, even if it never gets executed, it's a bad code smell. It's just stinky and horrible. Yeah.
So this actually the other thing I hate about find bugs. My IDE already told me about all this shit like ages ago. So like find bugs is just like running. I've already cleaned up all this because every line of code I test, my IDE is doing this already.
So why is that a problem with find bugs?
Because most of find bugs value is pretty much gone, so it's pretty much all noise by the time it runs. Like it's gotten worse.
Well, so is your IDE running find bugs to do that?
What?
Is your IDE running find bugs to do that?
No, I mean IntelliJ is.
Oh yeah, IntelliJ.
It's unbelievably powerful.
Right, sure. IntelliJ has some plugins to do this. What? Lots of people. People love IntelliJ. A lot of JetBrains people in here. Yeah. Well, so and absolutely. The problem is that when you get to these data centers, you don't have when you're trying to run backends which build code in data centers, you're not running IntelliJ. So yeah, and sometimes IntelliJ works, but then you have developers who want to use Eclipse too, and you have developers who want to use Emacs, and you have developers who want to use VI. And I know, who cares about those guys? I do most of my coding in Emacs. So the answer is, and I think that you've touched on it, the answer is you have to actually make it easy for them. You have to make it so that the compiler is actually doing this stuff. Excuse me. So the strategy is to just make all the warnings into compiler errors, and I think I'm going to spend a slide summarizing exactly what you just said. You have to restrict the problems to the high-value problems so that you're not getting bugs that are not bugs, and you just turn those into compiler errors. And you provide a detailed fix, right? This is what IDEs do. You hover over it and it spits out a fix. So what do we have to do when we want to add one of these? Well, I've got a single source code base, and it's got a lot of zeros worth of code in it. And so what happens when I want to fix this? Well, you got to fix all of the bugs and then turn it on in our single compiler for everybody. And that's somewhat challenging. But this, as you point out, this creates a whole sea change in the mentality of the average Java programmer. If you surface these sorts of problems at code review time instead of at compile time, we did a survey, needless to say. And if you surface these kinds of problems at code review time instead of compile time, 85% of people are likely to say, oh, that wasn't really much of a problem, and why are you bothering me with it now? And 14% of people are likely to say, oh, that was a problem, thank you for catching it. And 14% is not really a very good rate of return for something that you're imposing on everybody. But if you surface it at compile time, oh, IntelliJ already told me about it. All of a sudden, people actually like to see it. And so all of a sudden, coders actually love static analysis. And 70% of the coders we talked to said, oh, thank you, compiler, for finding that for me. That was great. Now there's an extra round of testing I don't have to do. So, it's as you point out, what you have to do is put it in the compiler. So we did that, and we wrote a system to extend Java-C to do that. And I should have apologized up front for saying this is a bit of a higher level talk than a lot of the talks so far. I'm not going to deep dive down to the assembly level in a lot of these. Java-C has a tree API, and we created an API over it that is very simple and very fluent and allows you to match patterns over that tree. And it's so simple and fluent that actually a lot of our users have been employing it in order to write their own checkers. So if the internationalization team comes up and says, oh, we want to check for this because this is a common internationalization bug, they can actually write their own checker to do it. And if the security guys come up to us and say, okay, well, we've added, we've got some tainting issues that we want to deal with, they can add pattern matcher to do that. You can turn it on per project. So if you've got project-specific passes, then you can do that. And people can write their own, which is nice. It's available open source. There's the URL. It's called error prone, which I think I may have not mentioned on a previous slide. And it's, as I said, it's a very, very simple API, which isn't necessarily good for people in this room, but it is very good for people who just want to write their own checker. They don't want to learn what bytecode looks like, right? They don't want to learn all the details of various things. It's a very simple AST checker, and you can say something very simple like, if there's an array and you call equals on it, then you match the pattern in the AST, right? Very, very straightforward. If it's an array type and you're calling the method equals on it. That's always a bad idea because it's reference equality and people expect deep equality, so you want to ban it from your source base. And that's all you need to write to match that. And it's very, very short and very, very simple. And so these checkers are really, really small. And if you go to the URL I pointed to before, you'll see that people write a bunch of these, and they're like, with all the Java boilerplate, they end up being 50 lines of code, but most of that is declaring the class and the import statements and things like that. And then you just have a way of expressing, hey, please fix this. What kind of fixer do you use? Well, that's also very easy. Suggest a fix that you use array.equals instead, and that you add an import of Java util arrays. It's a really straightforward and simple API. So we've been very happy with that, and we've had a lot of good results on it. Which leaves the other problem, which is how do you fix a code base with n lines of code when you want to get rid of these problems? Because as soon as you turn them on in the compiler, what's going to happen is that everybody, because you have a single JDK, everybody's code will start to break. And you can't break everybody's code, and you can't run sed. But you actually already have the tool to do this, right? Because I have these suggested fixes. And we have lots of machines, and we own the compiler, and we have the giant source base. So all we have to do is write a MapReduce that runs the compiler on all the code, finds all the instances of this, and applies the suggested fix. Yes?
So how does that work when the semantics have changed in the past, like the array equals versus deep equals?
Well, remember where I said you could run all the tests? You run all the tests, and every change has code review. Well, you got to send these out, and maybe you have 500 of these. So what you need is actually an automated tool to figure out who gets the code review, send the code review out to them, and split this single change you've made up into lots and lots of different sub-code reviews so that the person who owns the code can actually say yes or no to it. So we actually have infrastructure to do all of that. And it's actually kind of neat to watch it at work because you can make you can run this, make a single change over n lines of code where n is really, really large, and send out the reviews and have this all done inside of a day. And so you can do mega fixes. It's really neat.
And all your infrastructure is open source, right?
This is. This is partially a recruiting talk, which I will mention again. Yeah. We are actually, well, no, we will probably have announcements about stuff like that. Some of our infrastructure is open source. I did just mention that the matcher is open source. So you can, and it actually goes beyond these simple fixes. You can actually you can do lots of different kinds of changing of the code. If you have this sort of infrastructure, you can do other kinds of automated fixes across the code base. You can deprecate things across the code base and run one of these things and change them all to the new supported API. You can do refactoring and renaming across the code base, and we have dedicated libraries people who have actually leveraged these APIs to do this. And we make open source and available to the public whatever we can. So we do the best we can.
So, sorry.
Yeah.
So each one of these changes gets eventually reviewed by a human? Or?
Yes and no. If it's sufficiently simple, we actually have people who, so the repository is a single code base, so it looks like a file system. And at each level, you can have a set of owners. And if you are a root owner, if you can approve changes across the entire file system, across the entire repository. So root owners can actually approve. If a change is sufficiently stupid, which if you could run it with sed, and you didn't need to do this, then often a root owner will just say, that's fine, just apply it to everybody and it'll be fine. But yes, for changes that might be breaking, array.equals is a potentially breaking change. That's one of the reasons why we haven't actually enabled that one. It would actually have to go through a person looking at it and saying, yes, that's okay. Yeah?
So it just seems you've got you test after commit as opposed to before. And
No, you're supposed to run all the tests before the commit in practice. In practice, you do run all the tests before the commit. And in fact, a lot of people we have the notion of pre-commit guarantees, pre-commit checks. And a lot of teams, actually, we do have the built-in notion that you have to run the tests. And there's actually a check you can make to make sure that the person has run the tests. It queries the backend to, oh, am I running late? Was that what that was? I heard a ding. Oh, okay.
Somebody's installing software on the Mac.
Yes, so, right. So the question was tests. And we actually can fire off a bunch of pre-submit tests and say, please run all of the tests for my project. And before you submit, it can actually check to make sure that you've done that. So
It
that,
sounds like something.
and some teams require that. What?
Sounds like something optional. You can't do it.
The team can do it. You can enforce it over a part of your code. If you own a part of the code, the team can actually say, I want this enforced over that part of the code. So like, if you make a check-in in this subtree, why wouldn't you always do that? Well, it depends on, why wouldn't you always do that? You know what? I don't work on one of those teams. We do that on my team.
For those who don't, you've got that, and then you've got things automatically changing the code base. That seems like a rather dangerous combination.
Yeah. It's certainly that's something that people do because it's certainly the fact that there are people changing the code out from under you, that's an incentive. I'm not going to deny that. Yeah.
So even if you do test before you push, there's still a race. Two people can push incompatible changes. So what do you do when there is a post-push test failure?
Well, you have to run the tests at every single check-in. And if one was going to make everything fail, and then if one provided half of what made everything fail, and then the next check-in provided the rest of what made everything fail, well, that doesn't happen really all that much in practice. Usually it's one person checked something in that broke everything. And so you just identify what check-in that was.
So
Yeah.
you just blame the last.
You blame the last person. And if it wasn't them, they say, this isn't my fault, this is somebody else's fault. Like, people know what they broke, by and large. Yeah. Yeah? All right? Okay. So the result is that, as I said, coders do like static analysis. That we've solved all of these problems. So I'm going back to talking about static analysis now, although I think our testing and building situation is actually a very interesting one. There's a good signal-to-noise ratio because we pick only high-value warnings and we turn them all on. It finds important bugs because as you were typing it, even if you think, oh, that code isn't going to be executed, as you type it, even if you are finding bugs in testing code or logging code, where traditionally retroactively applying static analysis, just a second, will not solve the problem, then but you do care about it as you're typing. Sorry, what was?
How do you choose which ones are the high-value warnings? Are you actually asking, like doing?
We do surveys. That's part of it. When we turn on a warning, we have a very small number of warnings that we've actually turned on, to be honest with you. One of the things we do is we identify all of the bugs in the code base, and we look through them, and if they all look wrong, then that's an obvious thing to do. Another thing to do is just things that are so ridiculously boneheaded that you never want to do them. Like if p, we don't actually have this one turned on, but if you see something like if p equals null, p.x, that's obviously going to be wrong everywhere, unless somebody just wants to throw a new null pointer exception, in which case you identify the code and you change it to throw new null pointer exception. If you don't understand a bug, we make sure that the framework tells you how to fix the bug, and it's no longer outside your workflow. It's now part of the compiler. And part of the reason why I wanted to come here was, that's the next slide. What do we do with the more intensive errors? What if you can't run it in every compiler pass? What if it's interprocedural analysis? What if it's find bugs, which actually requires you to analyze a big jar file full of all of your code? Well, that requires whole program analysis or something like that. It might be lower value, right? Yeah. So we're actually working on a separate pipeline, which we turned on today, I found out, that will allow you to opt into more expensive warnings and surface them in code review. So the code review tool will actually automatically send out a review of your code that expresses, oh, hey, you have this bug and that bug, and then you can feel free to ignore it or not, depending on whether you think it was worthwhile or not. All right. There's lots more work to do on this framework. Those of you who are interested in looking at it, please do. It's somewhat primitive on how it generates fixes. There are more warnings that need to be added to it. As I said, we've only turned on a very small number so far. There are actually more that exist. But then once something exists, you have to do the comparatively painful step of fixing it across the code base. And making it more flexible, right? So the infrastructure right now is somewhat targeted to the warnings that went into it. And there are a lot of unpolished edges. So another thing that we have to do another thing that we have to do here, which is one of the things I wanted to mention in this forum specifically, is that it might be nice to standardize this. It's built on top of the tree API. The tree API changes at every Java release. We have to scramble to keep up. It might be nice to have a more flexible and standard way of interfacing with this. So that was the part of my talk that talked about Java-C and our coding and building process. I was going to talk about testing. Is the clock at the back of the room accurate? Just so I know, it's the 27 after. Okay, yeah. So I only have 15 minutes. Yeah.
You probably know about that, but in JDK there is a kind of new option in the compiler.
The checker API.
Yeah.
What?
You can attach a plugin to the compiler in JDK.
Yes. Yeah. I actually only found out about that today, to be honest with you. But I will have to. So I spent 20 minutes prepping for something prepping for an ask that might already be there. All right. So I only have 15 minutes left. So I'm going to power through. My next thing was going to be what we do for testing, which is a lot more JVM oriented. And I was going to give this short shrift anyway. I will give it even shorter shrift. Basically, we do a bunch of dynamic detection based on stuff in the JVM. We do a bunch of dynamic analysis based on JVM level changes we've made. And this stuff is interesting, but I don't have time to talk about it, so I'm going to skip it. The what broke my test detector is an interesting little mini talk in itself. So what then? You check in code, it automatically runs the tests. You have to do a lot of stuff to compile. At every check-in, I'm going to skip the details, then you deploy, and you have to monitor your application. All right, So this should be. And this is where I sort of change direction for the talk and talk a little bit more about the JVM level. As I said before, programmers have very little insight into what their code does. They write, their little chunk of the code, and they don't write the libraries, and they don't actually, in our scenario, they are often not responsible for deploying their code, so they don't even get to see what happens in production. What will happen in a lot of the times in our case is that they will hand it off to somebody who deploys the code, they will deploy the code, something will break, and the people who deployed it will have no idea what broke, and so they can't actually fix it. And so there's this long back and forth between the people who deploy it and the people who wrote it about fixing the problem. And they're also not responsible for other services, things like storage backends. So they don't have insight into what their code is doing. So I'm going to talk a little bit about what we do to try to give them that insight, and I'll talk a little bit about the kinds of performance monitoring that we do based on our JDK. And the key takeaway, I think, is that we want always on no overhead monitoring and profiling. And I thought, let me just make sure, yeah, okay. So imagine you're commercial profilers don't do that. No profilers I know of do that. Fact of the matter, okay, yeah. Cliff is talking about Azul, right? I'm talking about like mere mortals. I guess it's kind of weird for somebody from Google to come up and talk about being a mere mortal when he just talked about changing, however many million lines of code in a second and a half, right? So, but commercial profilers tend to be very, very intrusive. And if any of you have used JProfiler or HProf or anything out there, they have a real significant measurable overhead.
Can I say one thing here? Java mission control.
Yeah, that's good.
Does it provide useful enough information, I guess, is one question. A lot of the metrics that come out are very coarse. So for example, how do you get a detailed profile of where the hotspots are in your application?
Java mission control, Java flight recorder.
Does that work on .jrocket?
That works in Java 8.
Oh. Do I have to buy it from Oracle?
You can use it for free outside production.
Okay, I guess I haven't, outside production. Okay, yeah. All right. So that might or might not be an option. I guess if we pay, then we can. So part of this is also, we've been doing this for a few years, and these are our observations. So it may be that Java Mission Control solves all our problems. I know there are things like GC history.
Also 7U40, by the way.
Sounds good. Oh, I know some of the things that go into 7U40, like native memory tracking, but I'm not familiar with all of them. Yeah, it was very, very coarse. Anyway, I want to get through this, so I'm going to talk about this, and maybe Java Mission Control will solve all my problems, and maybe it won't. One of the problems is that measurable overhead is unacceptable, but you actually do want detailed information about what's going on in your JVM. And it's tricky to aggregate results across multiple machines with any, and maybe Java Mission Control also solves that problem, I don't know. For those of you who have tried using things like JProfiler, you'll find that they tend to use things like bytecode rewriting and JVMTI, which have a very high overhead. You turn on HProf in any sort of reasonably multi-threaded program, and you can end up eating up 10 to 20% of your application. And when you have important latency requirements, eating up 10 to 20% of more CPU is not an option. It just isn't. And they also interfere with your program. Right? If you start instrumenting, you're interfering with the program, and interfering with the program is going to interfere with the measurements, and you're going to be measuring the wrong things. And that's the same reasoning as micro-benchmarks. There are JIT effects, there are code layout effects, and so on and so forth. And I'm sure everybody in this room is very familiar with the problems of doing micro-benchmarking in Java. Yes, so stack traces is one thing that we've had a really, really hard time dealing with. And the problem with the tools that exist for getting stack traces from the JVM, and I don't know, maybe Mission Control solves this problem, I really don't, is that profiling happens at, well, there are several problems with it. Profiling happens at safe points. I should phrase this carefully, who knows what a safe point is? Excellent, I don't need to say so. Profiling happens at safe points. So that's very, very specific places in your program, loop back edges, method entries, method exits. The stack point gathering tools, like get all stack traces, that kind of thing, it doesn't actually say what's running. It says what it's not blocked, right? So you could have 100 threads that are runnable, but you could have 4 cores. And so there could be some serious contention issues there. And it doesn't account for GC time, which is also annoying. And these are all well known and well understood. There was a good paper in PLDI 2010 that sort of discussed some of these issues. But ultimately, that doesn't work at scale. It doesn't work for real applications. And we had to build a profiler that doesn't have these problems. Azul already did it, so Cliff already. But it turns out there's support for most of something that looks kind of like that in the JVM that is sort of half supported and half abandoned. It's in a very, very strange medium state, and I'm sure that I'm insulting somebody in this room, so I apologize. There is an undocumented JVMTI call that was in the JVMTI standard for a second, and you can actually look at the JVMTI changelog and see that it was put in and then taken out. That can be called at any time. It doesn't have to be called at save points. And it doesn't have to instrument the code. You can use the sigprof timer on Linux. Just fire off every once in a while and gather it. And it actually does report time spent in GC. And we've had to extend it in a few different ways to make it useful for us. One is that the rate of I have no idea what's going on here reported by async get call trace is actually really high. So we had to add a bunch of heuristics to try to figure out what was actually going on at that point. We also had to extend it to report native frames. I don't know, I mean, those of you who were here yesterday will remember my full-throated defense of JNI in Java. Well, the reason I did that is because we have a lot of JNI at Google. We have a bunch of people writing C++ code. We've got client libraries that need to be shared across C++ and Java. So we have a substantial amount of JNI that we run. So we did that, and we built the profile around this. And the upshot of that is that there's much less overhead than traditional sampling. You get 10 or 20% overhead from even doing sampling profiling, and it reduces down to 0. And it profiles the running threads. It actually will profile which threads are running. And it's more accurate. And I had posted a blog post about this in 2007, and occasionally people sort of at a very steady rate over the last 6 years have said, will you put out some code for us? I knew I was going to be talking about it in public now, so I slapped together a little bit of code and I stuck it online. So if you want to play with a profiler that does more or less the right thing and works on the current JDK, you can look at that. All right, so that's sampling profiling, and there's sort of an intervening, how much time do I have? 8 minutes. There's sort of an intervening step between the previous slide and this slide that I should have probably stuck in a different slide, which is that I want to talk about aggregation too, because the tools that are out there don't do aggregation. It turns out that if you're running on a server, on a bunch of servers, or you're running your application on a bunch of servers, you can build up a pretty good sense of what your application is doing by looking at all of them and aggregating the information. So you get a little bit of a profile from here and a little bit of a profile from there, and profile a little bit of the heap from here and profile a little bit of the heap from there, and so on and so forth, and you do it a little bit at a time, and you get the information out of all of them. It doesn't actually interfere with their performance, but you can gather a really good view of what your application actually does. And so we've not just applied this to CPU profiling, but we've applied this to a bunch of other kinds of profiling. So for example, our heap profiler, we have a heap profiler. It has a counter when you do an allocation that decrements from 512,000 to 0 with a little bit of smudge in there. And every time it hits 0, it takes a stack trace, it associates it with the object you just allocated, and it stores that with the object. And so you get a sampling of the stack traces that were allocated in your application. And you go around to all of your, to all of your servers, and you ask for which one of these are associated with the live heap. And you can get a really good picture of where your allocation is happening in your live heap. And people use this to great effect to remove memory leaks and things like that. And it doesn't cost anything. It cost something when we tried to do it with bytecode rewriting. It cost something when we tried to do it with dtrace. It turns out if you go into the JIT and just have it, have a counter in there that decrements, then it effectively costs nothing to do this. Call trace profiling, getting a list of all the methods that get called. If you try to do it with JVMTI, with this particular one, people tend to know that it's going to cost something, because getting a list of every single method that gets executed costs something. But it turns out if you do enough engineering, you can get it to a single-digit overhead. And so you can have something that's relatively lightweight. We've even got an intern trying to take this approach and apply it to data race detection. You detect a data race on one field at a time. And you build up an aggregate over enough servers, and you can be reasonably certain with some statistical analysis, which we haven't done yet, in theory, that you're actually catching a meaningful number of data races. And detecting a data race on one given field turns out to be a tractable problem in terms of overhead, whereas if you have a data race detector and you're running it on your entire program, everybody who's run a data race detector knows that it has whole number multiples of slowdown. So we aggregate, and that's it. And you sort of start again, and you write some code. No. The only thing that I was going to say after this is I was going to talk very, very briefly about the fact that we do garbage collection work. And it was really only to point out that garbage collection, unless you go the IBM route or the Azul route, which I'm saying because there are IBM and Azul people in this room who are going to yell at me if I don't mention it, that GC is actually a real problem for a lot of people deploying code. It turns out that there's this meme that among Java programmers that allocation is cheap, which is true, but GC isn't cheap, and they don't really make that trade-off very well. And GC can stop your program for like 2 minutes. So we've actually been doing some work on the GC. It turns out that when we started to look at it, there was a lot of low-hanging fruit. So things like, we focused on CMS for this work, because when we started it, G1 wasn't ready for prime time. We're relooking at G1 now. Things like just balancing the number of threads to the number of cores available gave us a 30% speed up in young gen time. Things like, we looked at it and we realized that the giant full stop the world garbage collector for CMS, that is sort of the failover garbage collector, that was single threaded. So we parallelized it, and it turns out that if you've got more threads working on it, it goes faster. So we got some very nice speed ups from that. Parallelizing the CMS collector, the concurrent collector has a couple of really short pauses at the beginning and end of this concurrent phase. We were able to make them even shorter by parallelizing them. That code, I am happy to say, actually did manage to find its way upstream and was checked in last week. We implemented something that, one of the big problems with the concurrent collector, for those of you who know it, is that it seriously fragments the heap. We implemented something that when you do the initial mark or the final mark, it actually partially defragments the heap, and have gotten some really nice removal of full stop the world collections from that. It turns out that there are even some benchmarks that try to stress that fragmentation, and they fail when you do things like try to defrag the heap partially. We give back unused RAM to the system. It turns out Java's a bit of a RAM hog. So if you give back the RAM you're not using, you can actually get like 20% of your RAM back. And we did some stack allocation stuff that's very experimental, and if you want to talk to me about it, we can talk offline. The reason that I bring this up is because we are hiring for garbage collection. So if you want to work on garbage collection, please come up and let me know. Well, not come up to me afterwards and let me know. And so that is it. And the conclusions are fairly obvious for those of you who've been listening. And I think I am just about out of time. Oh, I'm even over time. So I should probably let Cliff go. And I'm glad I didn't have to go after Cliff, because Cliff is always way more entertaining than I am. So thank you very much.